Okay, now it's recording. And so we have our raw observations here, right? But what do scientists do? They look for patterns and trends. And so that's what I want you to do. I want you to see, are there any patterns in, whatever? And so take some time to think of a pattern. Sometimes recognizing a pattern is tough. You have a lot of observations. Sometimes the patterns aren't so clear, so scientists like to make graphs, to see if there are correlations between two variables, or sometimes they like to do other things. In this case, we wouldn't make a graph, we just look. But if you have some ideas, do you see some patterns? What are they? Tell me. Yeah, these are all O3 minus. That's good for the 8s. So fluorate, chlorate, bromate, iodate. What else? Yeah, okay. 2 minus to 3 minus. That's good. What else? Yeah, either 3 oxygens or 4 oxygens. And so one of the patterns is this L here, or this, have all 3 oxygens, right? Is there another class? Are you guys waiting for another? Yes. What time do you guys meet at? 2:30? Okay. We'll be done before then. All right, I'm going to speed things up so we can finish here. These have 3 oxygens. That's good. These ones have 4 oxygens. Okay, anything else you notice? Okay, yeah, the charge here, -1, -2, -3. Or another way to see the pattern might be this. You go -2, -1, and then it just stays -1, right? And so the charge appears to decrease. Well, what good are patterns like this? Well, there are 2 types of students I found. And all instructors hear this all the time, that that exam was nothing like the homework, or that exam is, those questions were, you never talked about that type of stuff. Well, it's because, their type of understanding. And so 2 types of understanding here. There are the people who just memorize these, right? And that's it. And so their whole universe of knowledge just consists of what they've memorized. And then there are people who look for patterns. The people who look for patterns will notice certain patterns like this. Therefore, if they get something that they've never seen before, so for example, I want the formula for borate, and then some people will say, hey, that's not fair. You never talked about borate, right? Why are we expected to know what borate is? Well, I'll tell you, there's some sharp students who will know what borate is because they know the pattern. How do they know the pattern? Because by the time the final comes along, they've looked at this so many times, they've read this, that these patterns start to stick out. The first time you look at it, there's no pattern there. But can you imagine looking at this over and over each week? Then you start to notice certain things, right? And so you start to notice, and so what would your guess for borate be? Even though you might know this already, but what would you guess? How many oxygens should borate have? 3. So I would guess BO3. Now, what would you guess the charge on borate? 3 minus, and then you're right. That's the correct formula for borate. And so there are people who are going to say, oh, that's totally unfair, but then there are people who are going to say that's totally fair. because it's a simple pattern, right? And simple patterns we use to make predictions, just like the ideal gas law. Ideal gas law is a simple mathematical pattern that we use to make predictions. Right? No different than this. But well, in a way, this is not a mathematical pattern. Okay, let me ask you what the formula for silicate is. Silicate is below carbon and to the left of phosphorus. Silicon. And so if I have silicon and I want to know what is the formula for silicate, you tell me what your guess would be here. How many oxygens do you? 4 oxygens and the charge? 4, and then you're right. That is the correct formula for silicate. And then arsenic. Arsenic is below phosphorus. What do you think arsenic might be? Now this is tricky because we don't have much to fill in the pattern, but let's just take a guess. Arsenate would be ASO5. It turns out, no, it's ASO4 and the charge 3 minus. And so that's why I said it's tricky. Yeah, you could think 3, 4, 5, but it's going to top out. So germanate below silicon would be GeO4, 4 minus. Arsenate is below phosphate, ASO4, 3 minus. Selenate, selenium is going to be Se, and you're right, that's exactly what it is. Selenate is SeO4, 2 minus. And so, we as chemists use different approaches. Sometimes we just memorize it, but going beyond memorization would be trying to find patterns and trends. The way you can find patterns and trends is like this, because we can't spell them out all the time. The way you do it is you're going through your notes over and over again. When you go through your notes over and over again, you start to fill in all the blanks and you summarize this. You don't just copy somebody, oh, this is the pattern, and copy it down and just memorize it. You see this over and over, and then you come up with patterns and you write it in your own words. And so that's something else I did with my notes. When I was going through them, I went through them so many times that I was able to make different connections. Connections that weren't spelled out in lecture, but connections, oh yeah, this is related to that, And all these things get into your subconscious or your conscious, and you can solve problems that you might not have expected to solve because you've never seen it before, right? But you just connected it to other things. And so this is the way we do science, the scientific method. And this is, well, anyway, speaking of the scientific method, let's take this to another example, and that's what we're going to be talking about next, and that's chemical reactions. How many types of chemical reactions are there? Like in Chem 4 or Chem 1A, how many types of chemical reactions did you deal with? 2, 3, 100, 1,000? Well, okay, let's spell them out. You guys are. Decomposition, it's 1. Combination, 2. Single replacement, 3. Double replacement, 4. Combustion, 5. Acid base, 6. Redox, I heard, 7. Is that it? Or are there more? There's got to be more, because how many chemical reactions are happening on Earth here? A lot, right? And so what are you going to do? Are you going to memorize thousands and thousands of chemical reactions? That's what some people do in organic chemistry. They just memorize each reaction. But other people look for patterns of reactivity. What do you want to do? You want to memorize them individually? Thousands and thousands of chemical reactions? Or look for patterns? You look for patterns. And so how many major types of chemical reactions are there? Well, I've looked at it. I've looked at chemical reactions over and over and over again, right? Looking at the acid-base decomposition. I noticed that some decomposition aren't like other decomposition. In fact, there are 2 categories of decomposition. Have you noticed that? Probably you haven't noticed it because you haven't looked at it as many times as I've looked at it, right? But this is the advantage of doing this, this repeated review of your notes. This repeated review of your notes, you'll see, maybe we should subdivide those. But then even if you subdivide those, one category fits this type of reaction better than this, right? I wasn't the first person to notice this, but, and I'm just using things, but there aren't that many major types of reactions. So let's look at chemical reactions next. And this is the topic we're going to spend most of this week talking about. And if we look at the major types of chemical reactions, we see that there are only 3 major types of chemical reactions. And so if you take, some of those decompositions, some of them belong into this type, some of them belong into this type. So some decomposition reactions actually belong in this category, which we call metathesis. I'll talk about what metathesis is later, but essentially it's double replacement. And then some belong in acid-base, and some belong in redox. And so if we take all those thousands and thousands, of chemical reactions, we can categorize them into basically one of these 3 types of reactions. All right. Like I said, this comes from observing. So what we do in science is we do something called data reduction. Have you ever heard of data reduction? There are books written on data reduction. And the books just take, all your raw data, and you can have pages and pages of raw data, and then just try to simplify it, reduce that data. So for example, you could have pages and pages of graphs and numbers for gases. What happens when they change the temperature, what happens when they change the pressure, etc. And so you take all that data on gases and then you reduce it to one simple equation. That simple equation is the ideal gas law. Or if you take very, very sensitive measurements, you might come up with a simple equation called the van der Waals equation, for real gases, because you'll see things don't always behave ideally, right? And so that's part of the data reduction. Well, the same thing. We take all those chemical reactions and we reduce it down to these three categories, and this is what we'll talk about. And so once we have these categories, what do we do? Well, once we have this pattern, we're going to stop the pattern. We're not necessarily going to call it a law. And we're going to use this pattern to make predictions about what we expect for the properties. Products, sorry. What we expect for the products. And so by recognizing these patterns, we'll use the patterns to predict when I mix this reactant with this reactant, what do I expect to happen? Okay, we aren't really getting into the theoretical versus this is the 2-pronged approach. So we're approaching it from the observations. Now, what if I said, if I take this chemical and mix it with this chemical, you tell me what the products are going to be. Are you going to use, let me go back to quantum mechanics. I'm going to go to quantum theory and predict what the products are going to be? Yes? That would be great, and lots of people are trying to do that, exactly that, because if they can predict the products quantum mechanically, then they don't have to do a lot of experiments. They can just do it all on the computer and figure out what should happen, right? But is that something that's easy to do? If you wanted to prove, like if I said, prove to me that chlorine is a green gas quantum mechanically, can you do that? Or prove to me why chlorine should be a green gas and oxygen's a colorless gas, quantum mechanically. No. And so what we do is, it would be great. Yes, that would be great to do. But we can't predict that for everything. Some people think we can predict that for everything. That's why there's no memorization. These people are advocating no memorization. But for us, we got to take a lot of observations, and we have to have some observations memorized in order to do this. But anyway, we'll start with metathesis reactions tomorrow. Take a look at the PowerPoints on the website, and if you can hand in the handouts and your